Neptune sits at the edge of everything we know, 2.8 billion miles from where you are right now. So far that the sunlight reaching it left 8 minutes ago from Earth's perspective. The team used 3 primary facilities. The Very Large Telescope in Chile's Atacama Desert, one of the driest places on Earth, where the atmosphere above the summit carries almost no water vapor that could absorb the infrared signal. The Keck and Subaru observatories on Mauna Kea in Hawaii, operating at nearly 14,000 feet of elevation where similar conditions prevail. And NASA's Spitzer space telescope, orbiting above Earth's atmosphere entirely, providing measurements uncontaminated by anything our own planet's air might absorb or distort. Over 17 years, this network collected 95 thermal infrared images of Neptune. Each one required clear skies, precise instrument calibration, and hours of data processing to extract temperature values from a signal arriving across billions of miles. Each individual image was a data point. Only when lined up across the full observation period did the pattern become visible. The pattern was not what anyone expected. Neptune entered its southern hemisphere summer around 2005. Summer on Neptune means the South Pole tilts toward the Sun and receives more direct solar radiation than at any point in the previous 40 years. The physics of seasons is well understood. It applies to every tilted, orbiting world scientists have ever studied. More sunlight on a region means more energy absorbed. Temperatures rise. The thermal data from 2003 to 2018 showed the opposite. The global stratosphere, the upper layer of Neptune's atmosphere, had cooled by 14 degrees Fahrenheit. Not in one region, globally, across every latitude measured. During summer, scientists checked their instruments. They cross-referenced data across multiple observatories. The signal was consistent everywhere they looked. Neptune was getting colder while its summer was getting started. To understand what 14 degrees means at a planetary scale, consider this. The temperature difference between the peak of the last ice age and the warm period humans have lived in for the past 12,000 years is roughly 9 degrees Fahrenheit averaged across the whole Earth. 14 degrees is larger than that. On a planet already at roughly negative 350 degrees. Fahrenheit, in its upper atmosphere, a change of that magnitude represents a massive shift in how the atmosphere is handling energy. The stratosphere was losing heat faster than it was absorbing it. Something was actively pulling energy out of the upper atmosphere and venting it into space. None of the models scientists had built for Neptune included a mechanism capable of doing that during summer at that rate. They had no framework for it. They had only the data. Then the South Pole did something else entirely. Between 2018 and 2020, while the rest of the planet remained locked in the cooling trend, Neptune's south polar stratosphere gained 20 degrees Fahrenheit in 2 years. One location on a planet that was globally freezing had suddenly and intensely overheated. To sit with what that means, think about the temperature range between a comfortable 60-degree afternoon and the point where water freezes. That is 32 degrees. The South Pole gained 20 of those degrees in 24 months, at stratospheric altitudes, on the coldest large planet in the solar system. During a period when the rest of that same planet was recording its lowest temperatures in modern observation history. Scientists had no recorded precedent for polar stratospheric warming at that speed on any outer planet. Not Jupiter, not Saturn, not Uranus. Nothing in the catalogue of ice giant observations prepared anyone for a temperature spike this abrupt and this localized. The contrast it created was extraordinary. A blazing hot polar cap surrounded by the coldest stratosphere Neptune had shown in decades. The temperature boundary between those two regions would drive atmospheric circulation dynamics that existing models could not accurately simulate. Neptune already holds the wind speed record for the solar system. What happens to those winds when an extreme heat source appears at one pole, while the surrounding atmosphere remains in deep cold, is a question scientists are still working through. And while these temperature extremes were unfolding in the stratosphere, the visible face of the planet was doing something anyone with a telescope could see, or rather could no longer see. Neptune's clouds had been there for as long as modern telescopes had watched. The Voyager 2 images in 1989 showed them clearly. Long, wispy bands and compact bright knots of white against the deep blue background, all made of methane ice crystals formed in the cold upper atmosphere where temperatures drop low enough to freeze methane gas into tiny solid particles. Hubble began monitoring Neptune systematically in 1994. Year after year, the cloud features were present. Some years showed more activity, some less, but the clouds were always there in some form. Ground-based observatories tracking Neptune through the 2000s and into the 2010s documented the same ongoing presence. The clouds were considered a stable feature of the planet's appearance. When a team of researchers assembled the complete 26-year photographic archive from 1994 through 2020 and traced the long-term trend in cloud brightness, they found something that had been invisible in any short-term view. The brightness had been slowly declining for years, then sharply declined after 2015, and by 2019 had reached nearly zero. The cloud features that had defined Neptune's appearance for 3 decades were gone. The disappearance was missed in real time because any individual year looked like a quiet year rather than a catastrophe. It only became clear when someone stepped back far enough to see the full shape of the trend. 30 years of data showing clouds present in every image, followed by a relatively rapid collapse to nothing. By 2020, Hubble images showed a smooth, featureless blue sphere. No streaks, no knots, no structure, just blue. 3 separate and dramatic changes to Neptune's atmosphere: a global temperature collapse, a polar heat spike, and the complete disappearance of cloud cover, all happening across roughly the same window of observation. Any one of them alone would have demanded explanation. All 3 together suggested something fundamental about Neptune's atmosphere was behaving in ways the models had not captured. Scientists began searching for a mechanism that could connect all 3. The first real signal came from an unexpected direction. When researchers overlaid Neptune's cloud brightness record against the history of solar activity, a pattern appeared that should not have been possible across 2.8 billion miles. The Sun operates on an 11-year cycle. At solar maximum, ultraviolet radiation output is high, flares are frequent, and the solar wind is active. At solar minimum, everything quiets down. This cycle shapes conditions across the inner solar system. Earth's upper atmosphere responds to it. Satellite drag increases during solar maxima. Auroras intensify. The effects are real and measurable. Neptune sits 30 times farther from the Sun than Earth does. The total sunlight it receives is 900 times weaker. Scientists had assumed this extreme distance would render the 11-year solar cycle essentially irrelevant to Neptune's atmosphere. The cloud brightness data said otherwise. Neptune's cloud abundance was higher during periods of elevated solar activity and lower during solar quiet periods. The correlation was consistent across multiple solar cycles within the observation window, and the response in Neptune's clouds lagged behind solar activity peaks by approximately. The stratospheric cooling that began around 2003 altered the thermal structure of Neptune's atmosphere in ways that may have compounded the solar minimum effect on cloud formation. If cooling in the upper atmosphere changed conditions at cloud-forming altitudes even slightly, making them less favorable for methane ice to form even when seed particles were present. The combination of reduced seeds from solar minimum and less favorable formation conditions from the cooling trend would produce a more complete disappearance than either factor alone. The connection between the stratospheric cooling and the cloud disappearance is not yet fully confirmed. The causal chain requires measurements of atmospheric chemistry at multiple altitudes across time that only the newest instruments can provide. But the timing is too consistent to dismiss. Both events developed across the same years. Both were more extreme than models predicted. The overlap points toward a shared atmospheric system where changes in one layer propagate into changes in others. What remains harder to explain is the stratospheric cooling itself. The solar cycle correlation explains cloud behavior reasonably well. It does not cleanly explain a 15-year global cooling trend. Solar minima come and go every 11 years. A cooling that persisted through multiple solar cycles without reversing during intervening maxima requires something additional. Either a longer period variation in solar output, a chemical shift inside Neptune's atmosphere that sustained itself across more than a decade, or a separate mechanism entirely. One candidate involves the hydrogen in Neptune's atmosphere itself. Molecular hydrogen exists in two forms, depending on how the two atoms in each molecule are spinning relative to each other. These forms, called orthohydrogen and parahydrogen, absorb and release heat differently at very low temperatures. As Neptune's stratosphere cools, the balance between these two forms shifts, and that shift changes how efficiently the atmosphere radiates heat into space. Critically, the new balance can cause the atmosphere to shed heat even more effectively, which drives further cooling. A self-reinforcing loop where initial cooling leads to a hydrogen state change, that leads to more cooling, that leads to more state change. This mechanism is physically grounded. It has been discussed in the scientific literature as a contributor to Neptune's stratospheric behavior. Whether it is the primary driver, a secondary contributor, or a minor effect is currently unknown. Measuring the orthohydrogen to parahydrogen ratio in Neptune's stratosphere across different latitudes and over time requires the kind of infrared spectroscopy that only the James Webb Space Telescope can now deliver. The answer may already exist in Webb's archived data. It has not been extracted yet. To understand what Webb can see that previous instruments could not, it helps to understand what the earlier observation campaign was actually measuring. The 95 thermal infrared images collected between 2003 and 2020 measured heat emission from Neptune's atmosphere. They told scientists how much energy was leaving the upper atmosphere at different locations and converted that energy into temperature values. They were measuring one property, thermal emission, across one range of wavelengths. Webb measures something fundamentally different and complementary. It analyzes the spectrum of light coming from Neptune across a wide range of infrared wavelengths and looks for the fingerprints of specific molecules. Different gases absorb and emit infrared at characteristic wavelength patterns. Methane has its pattern. Ethane has its own. Hydrogen cyanide has another. By comparing the actual spectrum from Neptune against the known patterns of these gases, scientists can determine which molecules are present in the atmosphere and at roughly what concentrations. This is the chemical picture that the temperature record alone could not provide. If methane concentrations at key stratospheric altitudes changed between 2003 and 2018, Webb can detect the current state and help reconstruct what changed. If other heat-active gases shifted in abundance, those shifts appear in the spectrum. If the polar stratosphere's composition differs from the surrounding atmosphere in ways consistent with the heat spike, Webb can see that too. Webb's first Neptune images, released in late 2022, showed the ring system in clarity that Hubble had never achieved, and a sharp view of the polar region that opened new questions immediately. The scientific analysis of those images is ongoing. The spectroscopic data, the chemical Webb's planned operational lifetime extends to roughly the mid-2040s. For Neptune science, that means 2 decades of observation, covering approximately half of one Neptune season. A more meaningful fraction of the full seasonal cycle than any previous instrument achieved. If the stratospheric cooling trend continued after 2020, Webb will document it. If the polar region's temperature stabilized or reversed, Webb will show that too. If the clouds returned as solar activity rose toward the next maximum, Webb will watch them form in detail that no previous telescope could resolve. The answers are coming. They are just not all here yet. The internal structure of Neptune adds another layer to this story, because the atmosphere is not the only source of heat on this planet. Neptune emits about 2.6 times more energy into space than it receives from the Sun. The planet generates internal heat at a rate that dwarfs its solar input. This was confirmed by Voyager 2 in 1989 and has been measured multiple times since. The leading explanation is that Neptune is still radiating heat left over from its formation 4.5 billion years ago, when the accumulation of material through massive collisions deposited enormous amounts of thermal energy into the young planet's interior. But the rate of heat emission is high enough that formation heat alone may not be sufficient. An ongoing process may be contributing additional energy. The most likely candidate is differentiation, the slow settling of denser materials toward Neptune's core under gravity. As heavier compounds sink inward over geological time, they release gravitational potential energy as heat. This process has been running for billions of years and provides a steady internal heat source. This internal heat drives convection in Neptune's lower atmosphere, the deep layer below the stratosphere where direct measurements are hardest to take. Convection lifts warm material upward and draws cool material downward. On a rotating planet, this convection organizes into large-scale circulation patterns under the influence of the Coriolis effect. Neptune's extraordinarily fast rotation, combined with its intense internal heat output and its cold, methane-rich upper atmosphere, produces the 1,200 mile-per-hour winds that make it the windiest planet known. If something changed in how Neptune's internal heat was transported through the lower atmosphere during the observation period, that change could have affected conditions in the stratosphere above. A shift in convective patterns could alter how much heat reached the upper atmosphere and when. But the lower atmosphere is far harder to measure than the stratosphere. The instruments that built the temperature record were sensitive to stratospheric altitudes. What was happening deep below that layer where the internal heat meets the atmospheric column is largely invisible from outside. One of the most startling confirmed findings about Neptune's interior is not related to temperature or circulation, but to chemistry. Under the extreme pressures found deep inside Neptune, conditions exist that allow carbon atoms to bond into diamond crystal structures. Experimental physicists recreated the relevant conditions in laboratory settings by firing powerful lasers at hydrocarbon materials and confirmed the formation of diamond structures in real time. The diamonds form, become denser than the surrounding material, and fall inward toward the core. Diamond rain inside Neptune is not speculation or metaphor. It is a process confirmed in experimental settings and supported by the physics of the planetary interior. The diamonds likely form continuously, falling through the liquid interior, possibly accumulating near the core boundary. Whether this accumulation contributes to Neptune's internal heat output through gravitational energy release is an open question. But the process is happening right now as you read this, inside the planet whose disappearing clouds we are trying to explain. Neptune also has rings. They are nothing like Saturn's, where Saturn's rings are wide, bright, and made of reflective ice particles that catch sunlight. Voyager 2 confirmed this in 1989. 5 main rings, all dark, all narrow, 3 of them containing the denser arcs that had shown up in the occultation data. The arcs have names: Liberté, Égalité, Fraternité, Courage. Orbital mechanics predicts that a concentration of ring material should spread out into a uniform band within a few thousand years, because particles at slightly different orbital speeds gradually disperse. Neptune's arcs have persisted for at least decades of observation, and likely much longer. Something is confining them. The leading explanation involves Neptune's small inner moon Galatea, orbiting just inside the main ring arc region. Galatea's gravity creates a resonance effect that acts as a fence, pushing ring particles into the arc zones and preventing them from spreading freely. The mechanism is understood in principle, but the specific dynamics that maintain these particular arc configurations have not been fully reproduced in simulations. More recent observations have shown the arcs changing. Some portions have brightened or faded since Voyager 2 photographed them. The ring system is evolving. What it will look like in 1,000 years, whether the arcs will persist or gradually dissolve, is unknown. The rings are one more layer of complexity in a system that keeps revealing new complexity every time a more capable instrument looks at it. Neptune's blue color is the most visually immediate thing about it. The specific shade, deeper and richer than Uranus despite both planets having similar methane content, comes from the way methane gas selectively absorbs the red end of the sunlight spectrum and reflects the blue. This is well understood and confirmed. What is less discussed is that this color is also a diagnostic tool. The exact shade of blue encodes information about methane concentration, about haze particle density in the upper atmosphere, and about the structure of the atmosphere at different altitudes. A change in any of these parameters would subtly shift the color in ways that sensitive spectral instruments can detect. The photochemical processes driving the cloud story, ultraviolet radiation breaking methane into complex organics and haze particles, also affect the upper atmosphere's optical properties. More haze makes the planet slightly grayer. Less haze lets the deep blue dominate. A solar minimum reducing ultraviolet input would reduce haze production. A reduced haze layer combined with the disappearing methane ice clouds would leave Neptune looking distinctly different from its cloud-heavy solar maximum appearance. Tracking these color changes in detail is another line of investigation now possible with Webb's spectral precision. Scientists are looking for whether the optical fingerprint of Neptune's atmosphere shifted consistently with the cloud and temperature changes, providing another independent confirmation of the solar cycle mechanism. The size of what is at stake here extends well beyond understanding one unusual planet. Astronomers studying planets around other stars have found that the most common planet type in the galaxy is a category called sub-Neptune. Planets between roughly 1.5 and 4 times Earth's size, too large to be rocky worlds, too small to be gas giants. They orbit roughly 30 to 50% of Sun-like stars, according to the Kepler and TESS survey data. They are statistically everywhere, and our solar system has none in that size range. Whatever process produced them so abundantly around other stars did not leave an example here. This matters because sub-Neptunes are being analyzed with the James Webb Space Telescope right now. Scientists are measuring the atmospheric compositions of these planets, identifying the gases present, estimating temperatures, building profiles of what those atmospheres look like. The frameworks used to interpret those measurements are built on planetary models, and ice giant models are among the most relevant inputs for sub-Neptune interpretation, since they are the closest local analogues. Neptune has just shown that those models are incomplete in ways that matter. The mechanisms driving its cloud behavior, its stratospheric cooling, its polar heat spike were not included in the standard frameworks scientists apply to ice giant atmospheres. Using models that miss these mechanisms to interpret exoplanet atmospheric spectra introduces errors whose size is current. Every sub-Neptune spectrum analyzed today is filtered through assumptions that Neptune has shown to be wrong in at least some important respects. The photochemical cloud seeding sensitivity to stellar ultraviolet cycles was not in the models. If that mechanism operates on sub-Neptune's orbiting stars with their own activity cycles, and it almost certainly does in some form, scientists could be misidentifying atmospheric features or misclassifying atmospheric compositions without knowing it. Neptune is not just a distant curiosity. It is the calibration standard for a class of worlds being discovered across the galaxy. Getting Neptune right is a prerequisite for getting those worlds right. And getting Neptune right requires time, not decades in the way that most scientific problems require patience. Neptune time, seasonal time. One Neptune season lasts 40 Earth years. A scientist starting a career studying Neptune today will watch barely one season unfold before retirement. The full behavioral cycle of this planet, the complete arc from spring through summer, through fall, through winter, takes 165 years. No individual scientist will observe it. No single institution will fund a continuous program across its full length. The knowledge will have to be built incrementally, passed between generations, accumulated across careers the way the 20-year temperature record was built across multiple institutions and multiple countries before anyone could see the full shape of the trend. This is an unusual kind of scientific challenge. Most problems in planetary science can be addressed within a funding cycle or a scientific career. Neptune operates on a different timescale. The planet does not care about grant cycles or telescope allocation committees. It moves at the pace of orbital mechanics and seasonal chemistry and internal cooling processes that unfold over millions of years. What scientists have learned between 2003 and 2020 is genuinely significant. The solar cycle drives Neptune's cloud formation. The mechanism is photochemical and involves a 2-year lag between solar activity peaks and cloud abundance peaks. The global stratosphere cooled by 14 degrees during summer in a way no model predicted. The South Pole spiked 20 degrees in 2 years, with no recorded precedent in outer planet science. The clouds vanished for the first time in 30 years of continuous observation. These findings are real. They are confirmed by multiple instruments, multiple teams, multiple observatories across 17 years. They are published in peer-reviewed journals and are not contested as observations, only partially explained as mechanisms. The honest position is that the complete story is not yet written. The data represents one chapter. The explanation is partial. The future observations needed to complete it are underway with Webb and with whatever dedicated ice giant mission eventually gets funded and launched. Uranus and Neptune have been proposed as the target for the next flagship mission in planetary science by the National Academies of Sciences, Engineering and Medicine in their most recent decadal survey, the document that sets priorities for NASA science funding across a 10-year period. An ice giant orbiter with an atmospheric probe could transform Neptune science the way Cassini transformed Saturn science over its 13-year mission. Such a mission, if funded and launched in the coming decade, would arrive at Neptune in the late 2040s. It would begin operating during Southern Hemisphere fall as the season that started in 2005 approaches its end. It would carry instruments capable of measuring the atmosphere at altitudes and in wavelength ranges that no previous probe has accessed. It would be the first dedicated mission to Neptune since a flyby that lasted a few hours in 1989. In the meantime, Webb watches. The ground observatories continue monitoring. The archive grows. The cloud brightness data will show whether clouds return as the next solar maximum approaches. The thermal record will show whether the stratosphere has stabilized or continued its trajectory. The polar region will reveal whether the 2018 to 2020 spike was an isolated event or the beginning of a longer change. Every new image adds to a picture that only reveals itself over time. Neptune rewards patience more than any other planet in the solar system. It punishes assumption ruthlessly. It was hidden in plain sight on a star chart for months before anyone recognized it. It surprised scientists with its violence and color during a flyby everyone expected to be anticlimactic. It produced a 20-degree polar heat spike nobody saw coming. It erased its own clouds while no models 2.8 billion miles away. 165 years per orbit. A planet running on a timescale that makes human observation feel like a blink. We are watching. We are learning. The full picture will take longer than any of us will be here to see. That is the price of asking questions about a world that operates on deep time. The answers are real. They just arrive slowly, the way Neptune moves, at the pace of a thing too large and too distant to be hurried. There is a specific kind of strange in being the planet that math found before eyes did. Mercury, Venus, Mars, Jupiter, Saturn were all part of the ancient world. They moved visibly across the night sky, and humans watched them for thousands of years before understanding what they were. Uranus was spotted by accident in 1781 by William Herschel, who initially filed it as a comet. Neptune had none of that. No accidental observation. No ancient record. No curious notice by someone pointing a telescope in the right direction on the right night. Neptune exists in the catalogue of known things because two people trusted the logic of gravity more than anything they could see. Orbital disturbances in Uranus were real but small, tiny deviations from calculated positions growing over decades. It would have been easy to attribute them to measurement error. Adams and Verrier chose instead to take the disturbances seriously and ask what they implied. What they implied was mass, at a distance, in a specific direction. The math told them where. The telescope confirmed it. What strikes scientists today about that moment is not just the precision of the prediction, but the speed of the confirmation. Verrier sent his calculated position to Johann Galle at the Berlin Observatory on September 18, 1846. Galle received it on September 23rd and observed that same night. Within 30 minutes of starting to search, comparing the sky against the newly completed star chart of that region, he found an object that did not appear on the chart. It was moving. It was Neptune. 30 minutes. A planet billions of miles away, never seen, predicted only from orbital mathematics, confirmed in half an hour. The star chart detail deserves more attention than it usually gets. The chart had been completed just months before Galle's observation by Heinrich d'Arrest, a student working at the Berlin Observatory who had mapped that specific region of sky without any knowledge that a planet was hiding in it. Neptune appeared on that chart as an unremarkable point of light. It had been recorded, filed, categorized as a background star. This means Neptune was discovered twice. once by Darrist's chart and once by Gallet's comparison of the sky against it. The first time, nobody recognized what they were looking at. This is a different version of the same pattern that repeats in Neptune's story. The planet sitting in plain view while the tools to recognize it are not yet connected to the question being asked. After the confirmation in 1846, Neptune became a mathematical object more than a physical one for almost a century. Its orbit was refined, its mass was calculated. Its one large moon, Triton, was discovered by William Lassell just 17 days after the planet itself. But the planet's physical nature, its atmosphere, its internal structure, its weather systems, remained largely inaccessible. Triton itself added a mystery early. It orbits Neptune backwards. Every other large moon in the solar system orbits in the same direction as its planet's rotation. Triton orbits the opposite way. This retrograde orbit is nearly impossible to produce through normal moon formation processes. It almost certainly means Triton did not form around Neptune. It was captured, a wandering body from the outer solar system that came too close and got locked into orbit. Captured objects in retrograde orbits are gravitationally unstable over long time periods. Tidal interactions between Triton and Neptune are slowly pulling Triton inward. In roughly 3.6 billion years, Triton will cross what is called the Roche limit, the distance at which Neptune's tidal forces exceed the gravitational cohesion holding Triton together. At that point, Triton will be torn apart and its material will form a ring around Neptune, a ring far larger and brighter than any of the planets. The geysers appear to be driven by solar heating of a transparent layer of nitrogen ice. Sunlight penetrates the ice, warms the darker material below, converts it to gas, and the pressure eventually cracks through the overlying ice in a dark column. It is a kind of solid-state greenhouse effect, operating on a moon at the edge of the solar system. Evidence that even in the most extreme cold, energy finds pathways that produce dynamic surface features. Triton is one of very few places in the solar system with confirmed active geological processes. The shortlist includes Earth, Jupiter's moon Io with its volcanism, Saturn's moon Enceladus with its water plumes, and Triton with its nitrogen geysers. That Neptune's captured moon belongs to this list is one of many things that makes the Neptune system more interesting than its remote location would suggest. The question of what Neptune and systems like it look like in their full detail, at a level that requires years of orbital observation rather than hours of flyby data, is the question that makes a future dedicated mission so scientifically important. Voyager 2 gave scientists hours. Cassini spent 13 years at Saturn and transformed what humanity knows about that planet's rings, moons, and atmospheric dynamics. An equivalent mission at Neptune would return decades of continuous data across a genuinely meaningful fraction of a Neptune season. It would carry an atmospheric probe to measure composition and temperature at altitudes that remote observation cannot access. It would orbit close enough to the ring system to track changes in the arcs over years, rather than inferring them from the difference between a 1989 photograph and a 2020 image. The National Academy's Planetary Science Decadal Survey published in 2022 ranked a Uranus orbiter with probe as the highest priority flagship mission for the coming decade. Uranus and Neptune are both ice giants. Science gathered at Uranus informs Neptune's science, and vice versa. The Decadal recommendation reflects the scientific community's view that ice giants represent the most important gap in solar system knowledge, a gap that directly affects the interpretation of the most common planet type found around other stars. Funding decisions by Congress and NASA will determine whether that mission actually launches. The history of outer planet exploration is full of missions proposed, delayed, descoped, and occasionally cancelled. The political economy of large space missions does not always align with scientific priorities on the timelines that science needs. But the case for going is strong and getting stronger as Neptune's atmospheric surprises accumulate. Every anomaly detected from Earth is a data point in an argument for sending something back. Every confirmed surprise raises the value of the close-up investigation that only an orbiter can provide. The tools for reading Neptune at distance have also improved dramatically since Voyager 2's flyby. The Very Large Telescope and the Keck and Subaru observatories represent a generation of ground-based capability that simply did not exist in 1989. The adaptive optic systems now standard at major observatories correct in real time for the blurring effects of Earth's atmosphere, allowing ground-based telescopes to achieve image sharpness approaching what would be possible from space. The infrared detector technology available today is orders of magnitude more sensitive than what existed when Voyager 2 was designed. The Hubble Space Telescope's decades of Neptune imagery have built a continuous visual record that no single short-duration mission could provide. Hubble documented the disappearance of the Great Dark Spot. It tracked the appearance of a new dark spot in the Northern Hemisphere. It has watched Neptune's cloud systems evolve year by year since 1994. The sustained monitoring that reveals slow trends rather than snapshots requires exactly this kind of long-term commitment from an observatory that does not have to give up its time slot after one visit. The James Webb Space Telescope adds a qualitatively new capability. Its mirror is nearly 3 times larger than Hubble's. More importantly, it is optimized for the infrared wavelengths that carry chemical information about planetary atmospheres. Its spectrographs can analyze. What this means practically is that Webb can produce the chemical inventory of Neptune's upper atmosphere in a way that previous telescopes could only approximate. It can track whether methane concentrations change at different altitudes over time. It can identify the presence and distribution of photochemical products like ethane and acetylene that are produced by the same ultraviolet reactions that create cloud seeds. It can measure the temperature profile of the atmosphere at different altitudes by analyzing how specific molecular emission features change with height. This is the missing piece that the temperature record alone could not supply. Knowing that the stratosphere cooled by 14 degrees tells you something happened. Knowing which molecules changed concentration and by how much, at which altitude, tells you how it happened. Webb is now capable of providing that second level of information. The first published Neptune spectral analyses from Webb began appearing in 2023 and 2024. The data confirmed molecular species that previous telescopes had detected and revealed new features with higher precision. The scientific community is still processing what the full spectral datasets reveal about the mechanisms behind the documented temperature and cloud changes. The analysis is ongoing. One of the specific targets of current Webb observations is the South Polar Stratosphere. The region that heated by 20 degrees in 2 years remains distinctive in its chemistry. If the heat spike was associated with a change in the concentration of heat-absorbing gases at polar altitudes, those changes should be detectable in Webb spectra, comparing the polar region against surrounding latitudes. If the composition of the polar atmosphere is returning toward the planetary average as the spike dissipates, Webb will track that too. The monitoring will continue for as long as Webb operates. Its fuel reserves and instrument health projections suggest the telescope could remain productive into the mid-2040s. 2 decades of Webb observations of Neptune will cover nearly half a Neptune season. That is more continuous coverage by a single instrument than any planetary body beyond Jupiter has ever received from a space telescope. The picture emerging from this combination of ground-based monitoring, Hubble imagery, Webb spectroscopy, and the archival Spitzer data is more complete than what scientists had in 2020, when the initial studies of Neptune's changes were published. But complete does not mean finished. The full explanation for why Neptune's atmosphere behaved the way it did between 2003 and 2020 is not yet written. The solar cycle mechanism for clouds is well supported. The hydrogen state change mechanism for stratospheric cooling is physically grounded and testable. The polar heat spike mechanism remains the least understood of the three. Something concentrated a large amount of thermal energy at the South Pole in a short time, that something has not been definitively identified. The interaction between these three events, a global cooling, a polar spike, and a cloud disappearance, all happening across the same observational window, is the central puzzle. Whether they share a single root cause or represent three independent manifestations of a complex atmospheric system running outside its predicted behavior envelope is unclear. The models that could answer this question are being rebuilt using the observational constraints that the original surprising data provided. Science does this. It encounters something unexpected. It builds models to explain the unexpected. Those models generate predictions. New observations test those predictions. The models are refined or replaced. Knowledge accumulates across iterations. Neptune's atmospheric crisis is somewhere in the middle of that cycle. The initial observations produced the surprise. The first-generation explanations, like the solar cycle mechanism, are being tested and refined. The predictions from those explanations, for example that cloud abundance should increase as the sun approaches its next maximum, are being checked against current data. The deeper mechanisms involving hydrogen state changes and polar circulation dynamics are being developed and will need to be tested with data that does not yet exist. This asymmetry between how fast a planet can change and how long it takes science to understand why is one of the fundamental challenges of planetary research on the outer solar system. Neptune operates on timescales that do not fit human institutional rhythms. A funding cycle is 3 to 5 years. A scientific career is 30 to 40 years. A Neptune season is 40 years. A full Neptune year is 165. The scientists who built the temperature record from 2003 to 2020 were doing something genuinely unusual. Maintaining a monitoring program across 17 years, sustaining the institutional connections and funding streams needed to keep collecting data long enough to see a trend that no individual decade of observation would have revealed. That effort required a kind of scientific patience that is harder to sustain than any individual brilliant insight. The result was worth it. 17 years of data revealed something that changed what scientists thought they understood about ice giant atmospheric dynamics, about the reach of the solar cycle across the outer solar system, and about the adequacy of the models being used to interpret exoplanet atmospheres. One planet, 17 years, 95 images, 3 surprises that broke the models. That ratio, the ratio of what you learn to the effort required to learn it at this distance and on these timescales, is why the scientists who study Neptune keep doing it. The planet does not make itself easy. The distances are vast. The observation windows are narrow. The seasonal cycles are longer than careers. The mechanisms are complex and interacting and not fully understood even after 2 decades of careful monitoring. And yet, every time a new instrument looks at it with better eyes or asks a question that previous instruments could not formulate, Neptune answers with something unexpected, something that requires the existing picture to be redrawn, something that makes the scientific understanding of the solar system more accurate and the models used to interpret distant worlds more complete. Neptune was found by trusting mathematics over observation. It was understood, partially, by sustaining observation long enough to see patterns that short windows could not reveal. It will be more fully understood by combining everything learned so far with the new chemical information that Webb is now providing and the sustained long-term monitoring that a dedicated orbiter mission would make possible. 2.8 billion miles. A planet that hides in plain sight, changes in unexpected directions, rewards patience, and punishes assumptions. The investigation continues. The picture is incomplete. The next chapter is being written right now in the spectral data streaming back from the deepest, most capable eye humanity has ever aimed at the sky. Neptune is waiting to be understood. We are getting closer. There is something worth sitting with about what it means to study a planet whose full seasonal cycle outlasts human lifetimes. Science is built on reproducibility. You run an experiment, get a result, and someone else runs the same experiment and gets the same result. The confirmation matters, the replication matters, but you cannot replicate a Neptune season. You cannot run the experiment twice. There is only one Neptune, and it moves at the pace it moves, indifferent to whether humans have collected enough data to understand it yet. This creates an unusual epistemological situation for planetary science. The observations are real, the trends are confirmed. But confirming that a trend is real is different from understanding what drives it. And understanding what drives it at the level of mechanism, at the level of which molecules are changing, at which altitudes and why, requires sustained observation across the very timescales that make Neptune difficult to study. Scientists working on Neptune today are in a position roughly analogous to a geologist trying to understand Earth's ice age cycles with only 30 years of climate records. The signal is there, the pattern is emerging, but the full picture requires a longer baseline than any single human career can provide. This is why the 20-year temperature record built between 2003 and 2020 was so important, and why its construction required the kind of institutional commitment that does not come easily. Major observatories are... The case got easier each time Neptune surprised everyone. After the initial cooling trend became apparent in the early 2000s, the scientific interest intensified. After the polar spike of 2018 to 2020, the urgency increased further. Surprises attract resources in science the way they attract attention in most human endeavors. Neptune kept delivering surprises, and the monitoring program kept receiving the time it needed to document them. The researchers who built that record did not know in 2003 what they would find by 2020. They were doing the kind of open-ended observation that does not have a predetermined answer to test. They were watching to see what would happen. That approach is less common in modern science, which tends to favor hypothesis-driven research with clear predictions to test and clear endpoints to evaluate. Long-term planetary monitoring sits in a different category. Its value is in the accumulation, not in any individual observation. The parallel to understanding climate on Earth is direct. The global temperature record that scientists use to document Earth's warming trend was not built in a decade. It required sustained measurement programs maintained across generations, often by different institutions using different instruments, later harmonized and calibrated into a coherent, long-term dataset. The result is a record that reveals trends invisible to any short-term view, and that has become essential to understanding how Earth's climate system works. Neptune's temperature record is an outer solar system version of the same thing. Smaller, harder to build, covering a shorter absolute period relative to the planetary cycles it is trying to capture, but built on the same principle. Sustained observation is the only way to see slow change. And slow change on planets that operate on geological and astronomical timescales is where the most important physics lives. The difference is that Earth's climate record has the resources of every major national weather service behind it. Neptune's temperature record was built by a small number of research groups competing for telescope time at observatories that also support dozens of other scientific programs. The asymmetry in resources is enormous. The scientific importance of the result is comparable. What Neptune's story illustrates, among other things, is that the outer solar system is under-resourced relative to its scientific importance. The ice giants are the most common planet size in the galaxy, the most common kind of world that astronomers are now finding with their exoplanet surveys, and the class of planet we understand least well. We have sent one spacecraft past each of them for a few hours in the 1980s. We have built the rest of our understanding from ground-based and space-based telescopes operating at the limits of their sensitivity. The science that has emerged from those limited observations is remarkable. The 95 image temperature record, the 26-year cloud brightness archive, the solar cycle correlation, the Webb spectral analyses, all of it achieved at planetary distances, across enormous signal losses, using instruments not specifically optimized for ice giant science. Imagine what a dedicated orbiter would find. The Cassini mission at Saturn spent 13 years circling that planet and its moons. It discovered that Enceladus has a subsurface ocean venting water vapor into space. It resolved the complex structure of Saturn's rings at kilometer-scale resolution. It watched storms erupt and evolve over years, tracked seasonal changes in atmospheric chemistry, and mapped the internal structure of the planet through measurements of its gravitational field. Cassini transformed Saturn from a well-studied planet into an understood one at a level of detail that no amount of remote observation could have provided. A Neptune orbiter would do the same thing. It would arrive at a planet that has already demonstrated it is far more dynamic and surprising than its remote location implies. It would find things that nobody has predicted because nobody has been close enough to measure the quantities that would make prediction possible. It would carry an atmospheric probe that would descend into Neptune's cloud layer and measure temperature, pressure, and chemical composition at altitudes where remote sensing cannot reach, directly testing the mechanisms proposed to explain the temperature and cloud changes documented between 2003 and 2020. The scientific return from such a mission would extend far beyond Neptune itself. Ice giant atmospheric data gathered from orbit would provide the ground truth needed to calibrate the models used to interpret sub-Neptune exoplanet spectra. It would constrain the physics of photochemical cloud formation, of hydrogen state transitions, of internal heat transport in thick hydrogen-helium atmospheres. Every one of those physical processes operates on sub-Neptunes throughout the galaxy. Understanding them at Neptune means understanding them everywhere they occur. The mission would cost several $billion and take 15 to 20 years from approval to Neptune arrival, given the distances involved. In the context of what it would return, scientifically and in terms of the interpretation of thousands of exoplanet observations, it is among the highest value investments available to planetary science. Whether it happens depends on decisions being made now about funding priorities. The planetary science community has made its case through the decadal survey process. The rest is politics and budgets, which do not move on scientific timescales. In the meantime, Neptune keeps doing what it does, moving through its orbit, cycling through its seasons, absorbing faint sunlight and radiating internal heat and spinning its methane ice clouds into existence when the chemistry is right, and erasing them when it is not. The South Pole is still in summer. The polar stratosphere that spiked in 2018 to 2020 is somewhere in its recovery, or not recovering, or doing something else that has not been documented yet with enough clarity to describe. Webb is watching. The ground observatories are watching. The data is accumulating at the pace of available telescope time, which is never fast enough. When the next solar maximum arrives, cloud abundance should increase if the photochemical seeding mechanism is as important as the correlation suggests. That test is coming. The prediction is on record. Neptune will confirm or complicate it. And somewhere in the next decade or two, Webb's sustained spectral observations will reveal whether the methane and hydrogen chemistry at stratospheric altitudes matches what the proposed cooling mechanisms predict. The orthohydrogen to parahydrogen ratio, the methane concentration profile at different altitudes, the distribution of photochemical products above the polar heat anomaly. All of this is measurable with instruments currently operational. The data will come. Neptune's story is not finished. It has barely started in the sense that the most informative chapter, the one written by an orbiting spacecraft with an atmospheric probe and years of time, has not been written yet. But the chapters written so far have already changed how scientists think about ice giants, about the solar cycle's reach across the outer solar system, and about what the most common planets in the galaxy might actually be doing in their atmospheres while we study them from the equivalent of an enormous distance. One planet found by math, understood in fragments full of surprises, operated by physics that we are still mapping. That is Neptune. That is where things stand. The next image from the James Webb Space Telescope is somewhere in a data pipeline right now. Someone will process it. Someone will find something in it. The picture will change again in the direction of more complete rather than simpler. That is how it goes with Neptune. Every new tool reveals something the last one missed. Every new observation asks a question the previous ones could not formulate. The planet does not run out of things to say. We just keep finding better ways to listen. Neptune's position at the edge of the known solar system gives it a specific character in the history of exploration. Every mission sent toward the outer planets has had to pass through enormous distances with technology designed years before arrival. Voyager 2 was designed in the late 1960s and early 1970s for a Jupiter-Saturn mission. The extensions to Uranus and Neptune were approved incrementally, one flyby at a time, as each encounter succeeded and the case for continuing grew stronger. By the time Voyager 2 reached Neptune in 1989, the spacecraft had been in space for 12 years. Its computers operated on technology that predated the personal computer. Its communication systems transmitted data at rates that modern smartphones would consider too slow to function. And yet, the images it returned from the Neptune system were stunning enough to define what scientists understood about the planet for the next 3 decades. The 8.5-hour round-trip communication delay between Earth and Voyager 2 during the Neptune flyby meant that mission controllers could not react in real time to anything the spacecraft encountered. Every command had to be sent hours before it was needed. Every image sequence had to be planned in advance based on predictions about where Neptune and its moons would be at each moment of the flyby. The team had been rehearsing and planning for years to compress what science they could into the narrow window of closest approach. It worked. The images of the Great Dark Spot, the discovery of 6 new moons, the confirmation of the ring arcs predicted by stellar occultation data, the detection of Triton's geysers. All of it from a flyby that lasted hours, planned by people who had never seen their target up close and executed by a spacecraft that was already older than some of its engineers. The Neptune flyby was the last planetary encounter Voyager 2 made before heading out of the solar system entirely. It left a scientific legacy that sustained an entire field for 3.5 decades, until the ground-based monitoring campaign, and eventually Webb began revealing that the picture was incomplete in important ways. The completeness question in planetary science is almost always interesting. The question is not whether our current picture is wrong in detail. It always is, somewhere. The question is whether it is wrong in ways that matter, in ways that affect the conclusions we draw about how a planet works, and what that tells us about planets in general. Neptune's atmospheric changes between 2003 and 2020 represent the second type of incompleteness. The existing models did not just miss a detail, they missed a mechanism. The solar cycle's reach across 2.8 billion miles to influence cloud formation through photochemistry was not in the models. The possibility of a self-reinforcing hydrogen state transition driving sustained stratospheric cooling was not in the models. The capacity for a localized polar heat spike of this speed and magnitude was not in the models. When models miss mechanisms at this level, the conclusions drawn from them are unreliable in ways that extend beyond the specific case where the failure was discovered. If the photochemical cloud seeding mechanism operates on Neptune, it likely operates on every planet with a hydrogen-dominated atmosphere that receives ultraviolet radiation from a star with an activity cycle. That is a very large number of planets. The exoplanet count in the sub-Neptune category alone runs into the thousands based on current surveys. Scientists studying those planets are now working with updated frameworks that include the solar cycle mechanism for cloud formation. The Neptune observations have already improved the models used elsewhere, but the improvements are partial because the Neptune observations themselves are partial. The complete mechanism is not yet confirmed. The chemical measurements needed to nail down the specifics are still being gathered. This is normal science operating at the frontier. The knowledge is incomplete. The incompleteness is known and bounded by what observations have been made and what remains to be done. The path from current understanding to more complete understanding is visible if not yet traveled. What makes Neptune's case particularly instructive is the combination of factors that made the discovery possible at all. A sustained monitoring program maintained across 17 years. A team of researchers across multiple institutions who kept the program funded and operational. Telescope facilities capable of the required thermal infrared sensitivity. A large enough data set that the trend was statistically unambiguous by the time it was fully analyzed. The removal of any single one of these factors, and the result is either not discovered or discovered much later, with less confidence. This is a lesson about how knowledge accumulates at the edge of the solar system, not through individual brilliant experiments or decisive single observations, though those happen too, but through sustained, patient, unglamorous monitoring that accumulates data points one image at a time across years and eventually decades until the signal emerges clearly enough to be certain. The scientists who started that monitoring program in 2003 did not know they were building a discovery. They were doing the kind of careful, systematic observation that creates the conditions for discoveries to become possible. The surprise came from Neptune, not from any hypothesis they were testing. They were watching. Neptune showed them something. Neptune rewarded that approach with 3 separate atmospheric anomalies across 17 years, each more extreme than models predicted, together pointing toward a more complex and dynamic planetary system than anyone had characterized from the available data. The planet was not being perverse, it was being itself. The models were the problem, not the planet. Fixing the models requires more data. More data requires more observation time. More observation time requires sustained funding and institutional commitment. The loop closes back on the same challenge that has always defined outer solar system science. The distances are vast, the signals are faint, the timescales are long, and the resources available to study these worlds are always smaller than the scientific questions demand. And yet, here we are with Webb spectrographs already returning chemical fingerprints of Neptune's atmosphere at a precision no previous instrument achieved. With a decadal survey that ranked ice giant exploration as the top priority for the next flagship mission. With a scientific community that has demonstrated through the temperature record, the cloud archive, and the solar cycle correlation that patience and sustained effort at Neptune produce knowledge that reshapes how we understand planets across the galaxy. The next discovery about Neptune is sitting in data that already exists, or in observations being made right now, or in a mission currently being designed. It will arrive on the schedule Neptune permits, not the one we would prefer. 2.8 billion miles, 4 hours for light to cross it, 165 years per orbit, 40 years per season. A planet operating on its own timescale in its own way, full of things we have not yet seen. We are watching. We are learning. The picture is getting clearer, one observation at a time, at the pace this planet allows. That is enough. That has always been enough to keep going.